Joining us today at the Mechatronics Circus at Aalto University. My name is Heidi Henriksen. I'm with the Aalto networking platform. Welcome to the parallel session, Smart Moving Machines and Safe Operation, where we have researchers demonstrating 5 different projects. We're going to start with the first project, which is direct-driven hydraulics for large mobile work machines, giant seesaw test bench, Dolores. Robert Hermansson and Ville Nervanen are going to be presenting. Robert is a second-year master's student in mechanical engineering. He's currently doing his thesis on energy efficiency tests of the direct-driven hydraulics test bench, Dolores, which we'll be hearing a lot more about. Ville is a second-year master's student working on the Easy Zonal Hydraulics project. Today, he presents the Control Area Network Open Communication System used for data logging and control of the Dolores test bench. So I'm going to turn it over now to our 2 excellent presenters. If you have questions, please use the Q&A. We'd love to have you join us in the conversation at the end of the presentation. Thanks.
Hello.
We hear you. We see your slide. We don't yet see your slides.
Robert there. He will be starting.
Yes.
All right.
Hello, everyone. So I will share my screen now. Okay, can you see my screen?
It's all good.
No, yes. Great. So today, me, Robert Hermansson and Ville Nervanen will present you this Dolores direct-driven hydraulic test bench, which is seen here in the figure. So let's first look at the working principle of this test bench. So this boom, which is this 5-meter long part here, is rotated around this base frame with 2 hydraulic cylinders. So originally, this test bench was designed to study the DDH technology in a frame steering application of a mining loader. So that is where this geometry comes from. So in that application, you could imagine that the base frame is the other frame of the machine and the boom is the other frame. And this test bench came to Aalto in 2019, and this currently ongoing energy efficiency research is the first empirical research we are working on with this machine. So the main components of the machine are listed here. So parts number 1 and 2 here are the electric servo motor and hydraulic pump motor, which will provide the power to the system. Then there is this DDH valve block number 3, which will transfer the hydraulic power to 2 hydraulic cylinders. So parts number 4 are the 2 hydraulic cylinders. So there's 1 cylinder on the each side of the machine, which will work on the opposite direction and make this boom to rotate. Then we have an additional load here in place number 5, which we can apply there from 0 to 1,700 kilograms. Then one important component which is missing in this figure is the motor controller, which we have there an industrial frequency converter from ABB. So then about this size, so you can see that this is quite a large scale test bench for this laboratory conditions. So the total mass we are rotating here, including this mass of the boom and this additional load, is 2,400 kilograms, and the total mass of the system is 4,300 kilograms. So then this term direct drive hydraulics, so what does it mean? So the working principle of this direct drive hydraulics is that this hydraulic pump is controlled with electric servo motor, and the pump ports are straight connected to cylinder ports. So the cylinder motion is straight controlled by this electric servo motor. So the control is not based on throttling with the valve, but it's based on this pump control. And with this technology, it is also possible to operate the system vice versa. So for example, if we are doing a load lifting and load lowering with the cylinder, then when the cylinder comes down, the cylinder can work as a prime mover of the system. So the cylinder will rotate the pump, which will then work as a motor. and then this electric motor will work as a generator and produce electricity back to the system. So the benefits this technology brings is, the main benefit is this increased energy efficiency, which is mainly based on that the control is not based on throttling like in many traditional hydraulic systems. And then also this energy regeneration possibility. Then the controllability is one benefit, and the compact and flexible design that this system offers. So it brings this term decentralized hydraulics, which means that we can use these DDH systems as their own units. So like in traditional systems, we don't need many hoses and pipelines to transfer the hydraulic power around the whole machine, but we can use this as their own units. Okay, then current research we are working on, so the energy efficiency of the system. So what we are actually doing is try to illustrate here. So we are measuring the energy consumption in different stages of the machine. So starting here on the left side, we are first measuring the electric energy to the system, which comes from the electric grid. Then we will lose some energy on the each stages of the machine, which we will lose something to the electric drive, the pump, the DDH valve block, and the hydraulic cylinders. And finally, we will get some mechanical energy out from the cylinders. So we will measure the energy consumption in each one of these levels and study how the energy behaves. So the biggest benefit we would like to see with this technology is here between the pump and the cylinders. So because this DDH valve block is not an actual control valve, so there shouldn't be much of throttle, so the efficiency between the pump and cylinders should be really good. Okay, but that was a short introduction to the machine itself and currently ongoing research. So then I will turn to Ville, and he will tell more about this research methods, which include our measurement and control setup.
Thank you. All right, let's go to the next slide directly. So our whole system is CAN-open based, in a sense that all of our data is going back and forth from a singular CAN bus, and CAN starts for control area network, which is seen in automotives especially. So in the picture of the left, you can actually see the basic layout that we have a CAN bus. Basically, in the physical term, it's basically the wire that goes sequentially through every single sensor on our system. And it has some nice benefits as for, well, the cable management is really simple. It's just one wire, and all the data is in digital form. So we don't really have the problem of interference that you would have in a more traditional analog system. And most of our sensors are CAN-open compatible, so that when we plug them in, they will send their data in digital form directly, and we don't have to do any data conversion. Of course, we have a few analog sensors, like our torque sensor is analog. And for those sensors, we have the CR2033 input-output board, which will do the transformation from analog to 16-bit digital form, which we then transfer to our CAN-open CAN bus and read it from our computer. And of course, we don't only use the CAN bus to read the sensor data, but we also send our control signals to the frequency converter. So, and well, in the software side, if you go to the next slide, please. In software side, this allows us to make a database. We use this software called Canalizer, where we can create this database. As you see on the left picture, we assign each of our sensors with the unique ID. And when we assign the we assign the sensors with their signals, so that when we go to our Simulink side, where Simulink is actually what we used in our automated control, we can simply open and choose any signal we want to import to Simulink software. and it's really easy and fast to use. And lastly, from our control side, if you go to the next slide, please. This is our basic control scheme, so that we have manual joystick control where we can drive it to whichever direction we want. And then we have automated control in Simulink, which is position feedback based. So we read the cylinder position from the Dolores via CAN bus. And then we have a simple P control logic, which stands for proportional control logic, that we are comparing to the reference position input, which at this time it is a sine wave input, but it can be basically anything. And that logic then goes through the CAN bus to the frequency converter that will then drive the electric motor, and the cycle continues, and we achieve automated drive. And in the last slide, we actually have a video showing the Dolores working. Actually,
yes. So I start playing.
All right, very good. So here's some automated control first. And here you can see Roberto driving it with the joystick back and forth. We have a really nice control over the speed. We can go from 4,500 RPM to almost 0 RPM drive. This is our manual control box. For our automatic control, we actually don't use this one. We use the PC next to it. We change between whenever we drive manual or automatic drives. Here you can see our motor pump combo and a little bit of the cylinders. You can actually see the small wire sensor there. And if you look, you can see the purple wire. That purple wire is our CAN bus, where all the data is going back and forth. And yeah, in the last freeze frame, you can actually see this huge black steel box. That's our weight plates, 1,700 kilograms at the moment attached. But yeah, that is pretty much the end of our presentation. Thank you everybody for listening. And if you have any questions, please do ask.
Yes, thank you, everyone. It was a pretty short time to present this machine, so if you have any questions, we are happy to answer.
Thank you. I'm not seeing that we have any open questions in our Q&A. Does anybody have any questions? Please go ahead and post them to the Q&A. I see we have.
Heidi, I have one hand up.
Excellent. Please go
I
ahead.
have a question. So what is the weakest point of your test bed? So what is the weakest point of Dolores? What broke down during your experiments? And what you would do if you had 3 extra months?
Well, maybe that's maybe one big benefit with this hydraulics technology, that it's hard to break anything. Like, okay, in our test we have had some problems that we have driven it to the mechanical limit many times, but the hydraulics takes care that we don't break any components during that. So it's actually a benefit in this system that it's hard to break.
Yeah, it's really robust. We haven't actually physically broken anything.
Yeah, you are extremely lucky. I did my PhD like 15 years ago. We broke quite many things. So what about the Simulink? So how much you coded? You have shown some parts, like how you mark the different control systems. So how many controllers you have all together? And how well the Simulink was functioning? Did you have to write any add-ins?
Do you mean how many systems we have for the motor control?
So how many controlling points you have all together?
We only have 2. We basically have the joystick box, as you see in the video. That's the Parker box, which is used for manual control. Then we have the Simulink logic. So we basically switch between the 2 depending if we are using automated or manual control. Those are like our CAN open masters in a sense. They are the master nodes on our logic system.
And how many sensors you have?
Well, hold on. Over 20.
Yes, so something like over 20. Yeah.
All the pressure sensors, temperature sensors, flow sensors, torque sensor, position sensors. Yeah, over 20.
Thank you. Really smart replies.
Yes. Then there is.
Yeah, exactly. There's the question about do you have any data on the efficiency of the system?
Maybe not at this point. We don't have any graph to show, but what we have currently done the test, so it seems that okay, so the drive and the pump efficiency should be really good. So something about over 90%, and then this from pump to cylinders, this efficiency also seems to be really good. So it should be over 90%. Of course, it depends on the velocity and the load conditions, but it's looking really promising. But okay, maybe a little bit later we will have some reliable data on this efficiency.
Thanks, everybody. Thanks for the presentation.
Thank you.
Yes, thank you.
If you still have questions about this presentation, please go ahead and continue to put them into the Q&A because Ville and Robert can answer there as well. Our next presentation is Machine Vision Algorithms for Smart Intersections by Risto Ojala. Risto has worked in Professor Kari Tami's mechatronics research group with several smart mobility projects for nearly 3 years now. His research focuses on utilizing machine vision in traffic applications, especially in improving intersection safety. Risto has developed a proof of concept roadside unit, which is capable of transmitting road user locations to connected vehicles. His work tackles the problems of computationally lightweight road user detection, as well as reliable camera calibration for road user localization. Over to you, Risto.
Thank you, Heidi. Hello, everyone. So I'm going to shift the focus to smart mobility and talk a bit about how we can make traffic intersections safer by making them smarter. So let's jump right into it. So why are we focusing on traffic intersections? Well, safety-wise, traffic intersections are really problem areas in road networks, with approximately 20% of all traffic fatalities in the EU and US taking place in different kinds of intersections and junctions. And well, why intersections are dangerous, it's quite intuitive to understand, as these are the kind of special places in road networks where different road users actually have to cross each other's paths. So in order to get to where you want to go, you often have to actually get in front of someone, and this requires a lot of alertness and attention from the drivers. And we believe that using these new connected vehicle technologies, we can actually help the drivers in these areas. And well, in urban intersections, what's especially dangerous that many times the driver can't actually see the other road users in the intersection. This is because buildings or other obstacles are blocking their line of sight. And this is really the problem we want to solve, as it's of course very dangerous when the drivers are not able to perceive their surroundings properly. So what we propose is using these machine vision roadside units for example, surveillance cameras and traffic cameras in intersection areas that we can apply machine vision on and localize road users and send their positions over the internet to connected vehicles approaching the intersection. This way, if there seems to be a collision course between the connected vehicle and another road user, the vehicle can actually alert the driver, telling them, hey, you should watch out. There's for example, a pedestrian coming from behind the corner, going to cross the street. You should slow down. And this is really the idea of the system. And we are researching this right here at the Aalto campus in Otaniemi. We have a research environment set up on the left here. You can see our research vehicle, which is equipped with this additional screen we can use to convey information to the driver. On the upper right, you can see a camera installation we have, and on the bottom right, you can better see where the camera is actually located. It's on the side of the computer science building here at the Aalto campus. And what the camera actually sees is all the road users coming from the road that the red arrow indicates, and it can detect them, get their locations, and send the research vehicle when it's coming from the direction of the blue arrow, kind of warning the research vehicle to watch out for these road users. And okay, what are we actually researching with this environment is, well, a lot of our research efforts are currently going into working on the detection on the system. Actually, the capability of detecting the road users in the camera view, because this is of course a core usage of the system. So we are developing this algorithm we are calling MODECLA. That's short for motion detection and classification. And yeah, this algorithm can be quite well visually explained using the images that I've provided here. So let's go through them. On the upper left, we can see a frame of video, just a normal frame. And in step A, we are actually performing motion detection on this frame. So basically looking at pixels that are changing over time. And once we have these areas of motion, the result is quite noisy. So in step B, we are doing some basic filtering techniques to smooth out the detected areas of motion. In step C, we are fitting some bounding boxes to the detected areas of motion, kind of getting their on-screen coordinates. And in step D, we are actually using these bounding boxes to capture the locations from the original image. And finally, in step E, we are using a convolutional neural network to actually classify what these moving areas are. So we can see that this red box is given to the car, this cyan, this light bluish box is given to the people, and then this background is labeled as just miscellaneous background. And okay, next I'm going to show you a clip of what it actually looks like to run this MODECLA algorithm on a video from our research camera. And I'm also going to run another well-known detector called YOLO version 3 on the same clip to give you kind of a comparison of what it looks like. So here we go. Unfortunately, this comparison is a bit biased, as it just happened that the YOLO V3 saw these piles of snow on the back as cars. That is not regular behavior for it, but this was the data I had to work with for now. But ignoring that, the detectors seem to be working quite well, seeing the road users that are actually moving there on the road. MODECLA still needs some work done. It has some difficulties properly detecting overlapping road users. We can see it here as this car is passing the other cars. You can see they get this like same bounding box for the two objects. You can still see it here with the other cars. So only a single bounding box for the two objects. This is because the motion detection kind of, when the road users are on top of each other, the motion detection system as a kind of unified area of motion, and therefore only giving it a single bounding box. And this can restrict the usage of MODECLA in kind of very dense, high traffic areas. But other than that, the detectors are both working quite well and both giving somewhat similar results. But okay, so why are we doing this development of our own if the detectors are working somewhat as well in this application? Well, the reason really is computational load. So this YOLO V3, it's a very huge, deep neural network requiring a lot of computational power to actually run it in real time. So to run it at 30 frames per second, which is considered often real time, you need this big powerful computer that will cost you 1,000 to 2,000 euros basically. Whereas MODECLA is very lightweight, since the motion detection pre-processing helps its detection a lot, and you can run it in real time with this really small 100 euro single board computer. And of course, this price is a real important factor here, because if we want to actually have this technology on the road, it needs to be affordable in order to actually make installations. Okay, but this detection part was all about seeing where the road users are in the images. But we also want to know where the road users are actually in the real world, kind of put them on a map. How are we doing this? Well, we are able to achieve this as well, also using just a single camera, using the geometry presented here. Now that there's way too many details to go over right now, but the important thing to focus on is we can basically, here are the X and Y coordinates, and we are able to calculate those using the rest of the geometry, the other parameters. And in order to acquire the other parameters for the calculations, we have to calibrate the camera. And this is also something we are studying. How can we efficiently calibrate the camera so that the localization is accurate and reliable? And well, we have calibrated the research camera that we are using, and the result that it gives us basically can be seen here. So here is just on the left, there's just an image with a lot going on. So we have 3 people and 3 cars present. And then on the bottom right, you can kind of see the output of using these localization algorithms. So we have this chart that is like in world coordinate system. So you can see the y-axis is north and the x-axis is east. And the camera is here at the origin. So 0y and 0x. And the orientation of the camera is displayed by this drawing here, like an approximate orientation. And you can see that all the road users have been put on this map quite well. Visually observing, we can get quite good results with this localization technique. And well, to conclude, what we are developing is we are developing these machine vision roadside units for smart intersections, so that we can localize different road users in the area and actually send this information over the internet to connected vehicles, so that they get information of road users that they can't actually see. And this way they can alert the driver if they seem to be on collision course, so that the driver will know to prepare for the other road users. And what we are studying is these detection and localization problems, because the roadside units have to be accurate, fast, and cheap, so that they can be actually implemented in real road networks. Thank you very much for your time. Now I think it's a good time for questions.
I see we've already got a question popped up in the Q&A. Aristo, do you want to have a look at that, or would you like us to read it for you?
Could you read it for me, please? I was
Of course.
just trying to find it out here, but okay, I actually have, so I can read it out loud myself. I just found it. Have you looked into YOLO accelerators or implementations of it on resource constrained devices like micro YOLO or YOLO V3 Tiny? How far do you think you could push this to edge machine learning? And then there's a thanks, Risto, for a great presentation. Well, thank you for the compliment. And that is a very good question. This is a very technical question. So to maybe put it in other words, have we done any kind of optimization to sort of have we done any kind of optimization to run this YOLO V3 algorithm on this like lesser hardware? And the answer is yes. I'm afraid my answer is also a bit technical, but NVIDIA provides this Tensor RT optimization that you can use on these NVIDIA products, and this is what the version we've been actually using on the Jetson Nano single board computer. And with that optimization, you are able to get nearly 2 frames per second. Not close to real time, but you can still run it on this Jetson Nano. And we've also been using this YOLO V3 Tiny version, and it is a very good version, but the problem with that version in this application is really that it's not able to detect small objects because the neural network structure is made in such a way that it doesn't kind of handle different scales well. So it kind of only detects these objects that appear large in the image. And this YOLO V3 Tiny, you are capable of running at 20 frames per second on this NVIDIA Jetson Nano single board computer. I hope I was able to answer your question properly, Ville. Thanks for asking. And yeah, if you need some more details, please type in the chat. I'm going to answer the other questions now. So there's a question: how does the algorithm respond to different weather conditions? In most weather conditions, like rain, fog, it actually works very well. During nighttime as well, but there is really a problem with car headlights. So the motion detection, if it's dark outside and a car comes by, the car's headlights will light up the area, kind of making the motion detection think that there is motion when there isn't. Yeah, detecting cars in dark is very difficult for this molecular algorithm, but it has been able to actually detect people very well, even in dark circumstances. Another weather condition related problem is that very long dark shadows also can fool the motion detection, thinking that there is actually something there as the shadow is moving. So if it's like very early in the morning or very late, very late in the evening, but the sun is still out, the detection can be fooled by this dark shadow.
Thanks. I'm afraid we're going to have to pause here because we have more presentations coming. Aristo, I think that you can type an answer into our Q&A.
Okay, yes.
And that might be a really great way for us to continue that conversation.
Yes.
Would you like to pick up one more question from that list? And then we'll move on.
Okay, I'll pick this other question that was upvoted. So I think this work is really nice and the presentation as well. I have a more general question. How do you deal with pedestrians' recognition privacy? Thank you. Thank you very much for the good question. And in this case, we have contact. We basically, before doing this our research, we contacted a lawyer from the Espoo City about it, and they basically told that as long as we are not sharing any information that like how would I say, personal information, so basically images where people or cars can be identified, then that is okay for this privacy for this research. And for a more general kind of in actual application, I think that the privacy issues are kind of the same as with any kind of surveillance cameras in city environments. So of course there's certain processes to go through, but overall there are already quite a lot of cameras on the streets. So overall that shouldn't be a problem. I hope I answered your question, but now I think my time is up. I'll type a answer to all the other questions in the chat. Thank you very much for your interest.
Thank you, Risto. Our next presentation is electrically powered micro excavator with direct driven hydraulic actuators by Mikael Samatti and Juho Lehto. Mikael is a second-year master's student working on the fluid power group in mechanical engineering. He's writing his master's thesis on the topic being presented today to investigate the energy consumption of the direct-driven hydraulic system in excavator applications. Juho will be presenting research on micro activator equipped with direct-driven hydraulics with the aim to improve energy efficiency, especially compared to existing electrically powered excavators. Also, the suitability of direct-driven hydraulic systems for excavator use is evaluated in his research. Juho has been helping to build the test setup used in Mikael's master's thesis. Over to the presenters. Please go ahead and share your screen.
So hello.
We can hear and see you, and we can see your presentation. Thank you.
Okay. I'm not sure. Did I put the voice on?
That's correct. We can hear you just fine.
Okay. Share sound. No. Yes. So we will introduce our research machine, this JCB micro excavator with these direct-driven hydraulic actuators. And my name is Mikael Samatti. And then here is also Juho Lehto. You can say hello also.
Hello, hello. Can you hear me? I guess so.
Yes, yes.
Good.
Okay. Do you see the second slide?
It's all good.
Yeah. So I'm writing currently my master thesis, and I'm studying the energy consumption of this excavator. And we will use standardized GCMS digging cycles to measure the energy consumption of this excavator. The GCMS data cycles, they are made to measure the fuel consumption of diesel-powered excavators, but we are using them also to measure this electric consumption of this electric excavator. And we will execute the same cycles with this direct-driven hydraulic system and also with conventional valve-controlled system, so we can get reliable results to compare to each other. And here you can see basic drawings about the digging cycles. There is two different cycles, this digging cycle and then leveling cycle. And many questions have arisen during this research work, so in the future it will be interesting to research, for example, the system durability, oil filtering or cooling, also more about the controllability, and also about the safety features what will needed in the production machines. And it will be interesting to research what kind of intelligent functions can be used with these electric powered hydraulic circuits. Yes. And then Juho.
Yes. As said, I have been concentrated more on building the test setup, and I will tell you about the DDH implementation on the micro excavator. So gladly, Robert introduced you the main principle of the direct-driven hydraulics in his presentation, so I will concentrate more on the practical implementation in our application. About the modifications we needed to do for the excavator for the direct-driven hydraulics implementation, the excavator itself is JBC micro mini excavator weighing around 1,100 kilograms, suitable for garden use and similar kind of use. It was originally equipped with conventional hydraulics, and it was powered by diesel engine. But they were removed, and the direct-driven hydraulics was implemented so that the diesel engine original pump and original control valve block were removed, and then DDH pump packets were installed for boom, arm, and bucket cylinders, one for each, so 3 pump packets together. And I will tell about okay, nice. So then more closely about the DDH pump packets. DDH pump packets are built from DDH pump units, valve units, and sensors. Pump units consists of electrical motors, motor controllers, and pumps. The motors are Bosch records, 5.2 kilowatt water-cooled motors controlled by Recross Intradrive M motor controllers. the pump is external gear pump that also acts as a hydraulic motor, and the pump units are connected to DDH valve blocks. Valve blocks are specially designed for DDH applications, including anti-cavitation features and overpressure valves. Outputs of the valve blocks are connected to the stock hydraulic cylinders of the excavator. And to obtain the position data of the excavation, all boom cylinders are also equipped with position sensors. Also, the uppercase swing shown in the picture in the sensors group on the left is equipped with a sensor, but that is actually not that much related to DDH implementation because the swing is driven with conventional hydraulics instead of DDH. Yes, that's pretty much the system introduced.
Yes. Then we have the other part of hydraulics, the conventional part. There is fourth electric motor which runs the genuine JCB twin hydraulic pump, and the flow from that is used to control the other functions of the excavator, like the track motors, uppercase swing motor, dozer blade, and boom swing cylinder. And then there is this Danfoss CAN proportional flow control valve. And the power source for this electric motor is this 96-volt lithium battery. So the DDH motors, they are electric grid powered, but this conventional part of hydraulics, this is battery powered. And also this conventional hydraulic part, pump flow, it is used to recharge the hydraulic accumulators of the DDH circuit. Yes, and then about the control systems, we are using LabView to control the electric motors of the DDH system, and we also collect all the sensor data with LabView. And after that, we will process the data with MATLAB. And then about the energy consumption, what we know about it at this stage. So the fuel consumption of the diesel engine was measured before the engine removal. The fuel consumption was about 1.6 liters per hour, which makes about 16.2 kilowatt hours per hour. And after that, there was one research where the diesel engine was changed to electric motor, but the rest of the hydraulic system was original. And with that system, the energy consumption was about 3 kilowatt hours per hour. And now we have not yet the final results of the DDH system consumption, but a good guess is that the consumption is about 1 kilowatt hour per hour. And that is quite big improvement over the previous systems. And then for the last thing, I have short video about the excavator where you can hear and see the machine moving. So in this video, I'm controlling the machine manually. So we have two joysticks like in the conventional common machines. So, thank you. That was our presentation. Do you have any questions?
The Q&A is empty, but I could ask one question from you, Michael. So would you dare to drive this kind of machine in my garden now? So can you dig if you have to do it mechanically? Have you tried?
Can you ask again?
So I think so that the main purpose for use this kind of machine is digging
Yeah.
foundations for family houses, digging ditches for your garden, digging a ditch for a major tree. So did you learn to drive an actual machine? So how you compare this kind of digitalized version to the actual versions that they are using at the moment?
Oh, I have in home two real excavators or production versions with conventional systems, and I have driven them about 10 years. And this electric version, it feels quite same. It's very smooth to operate, and the control is very precise. So no problem to dig soil or holes for flowers or so.
Thank you.
Yeah, unfortunately, we have no soil in the laboratory, but we have planned that we make some kind of sandbox there. So,
yes. But meanwhile, we got a question to the Q&A. So can you find it? Can you see it, or do you want me to read it for you?
Yeah.
Or even have the second one?
Yeah, Jari Vepseläinen. Got any data to spare for energy efficiency chunky? What that means?
Yes, I could maybe answer that. At this moment, we have done some test cycles, and we have some assumptions about the energy efficiency, but it is pretty much what we told in the presentations, and we will get reference data when we will do the same test cycle with conventional hydraulics also. And it is maybe more interesting when we can give both test cycle data for you if you want to see them. But it really seems that we are getting really nice energy efficiency out of that system, but we can't give you right away the numbers yet because we have just started to do the test cycles, and we haven't that much yet analyzed the data we have collected.
Hey, thank you very much for the presentation.
Yeah.
I'm going to move on.
Thank you.
If there are some more questions in the Q&A, if the presenters would like to answer
Yes,
by
thank
typing
you.
an answer, that'd be great,
Yeah.
because we want to keep the conversation open.
Yeah, thank you for every questions.
Yes. Next, we have
Thank you.
detecting. You're awesome. Next, we have detecting trash and valuables with machine vision in passenger vehicles. Our presenter is Nilusha Jayawikrama, originally from Sri Lanka, who's graduated from his master's studies at Aalto, starting the PhD program this April. Nilusha is currently working on an anti-trash project in Karitami's research group to determine the cleanliness within the cabin of a shared vehicle. The presentation presents the work of his master's thesis and the methods and results using a vision-based framework to identify trash and valuables inside a passenger car. Over to you.
Thank you very much for the introduction, Heidi. I think everyone can hear me well. So I will talk a little bit about the work I did for my master's thesis in detecting crash and valuables in passenger vehicles. So
Nilusha, could you please move your microphone closer or turn up or speak a little louder? Thank you very much.
oh yeah, sure. Is it better now, Heidi?
Yes.
All right, thanks. Okay, so moving on. So just a little bit of a background on what I'm doing. So in the modern day, of course, everyone knows that there's been high focus on increasing the use of public transportation over private means in order to reduce traffic flow as well as vehicle emissions. And in this same domain, we have the developing concept of driverless taxis. However, in order to make sure that passengers use these types of transportation more and more, it's extremely important to ensure good levels of cleanliness in these vehicles. So cleanliness has two aspects. We have exterior cleanliness, which of course is not a major factor if you think about real-time maintenance. So a regular car wash could do the trick. But if you think of interior cleanliness, then it is absolutely essential that the cabin of the vehicle should be always clean. But but of course it poses a question as to whether there has been any initiatives on actually including a certain amount of automation to improve the efficiency of doing this type of maintenance. This begs the research question of actually utilizing a certain viable vision-based application to actually do this particular thing, and in the process to obviously have good cleanliness levels in the vehicles. So the motivation is basically to identify trash or valuables within the cabin of any shared vehicles. And then the purpose of doing so would be to then generate a cleanliness alert, and then of course ID the passenger responsible for either the mess or for anything that he or she has left behind in the vehicle. The objectives of the research were to actually implement a camera system that would be inside the vehicle cabin, and it would essentially capture the rear seating area, and then the images will be transmitted to a prediction model where the algorithm will classify if it's an empty seat or a clean seat, or if it contains any trash or valuables. And finally, the image dataset would be compiled so that it will, of course, be used for future development purposes. So during the literature search, the areas that we were mainly interested is to find out if there are any existing crash classification or detection applications and the types of models, and also the level of automation that has been implemented within this field in smart mobility. So these are just a couple of research work that I found with respect to the crash classification models. So I found out that neural networks was a very popular choice in this field, and also more traditional approaches, traditional machine learning approaches like via the Jones detection. But overall, there was like a very big range of accuracies. But generally, when they use neural networks, although it has been the popular choice, the accuracy usually suffered a bit because of the lack of training and also the lack of image data. So the research gap essentially lies in actually utilizing such a technique in this particular field of identifying crash and valuables in shared vehicles. So for the methodology, we utilized our own research vehicle in the Aalto premises, where the model would be trained for this vehicle and could later on be fine-tuned for other models in the future. And this is actually a circuit schematic of the setup inside the vehicle. So as you can see, the most important components are the Raspberry Pi and the camera, which together would capture the image and then store it for processing. And additionally, for demonstration purposes, I have also included an LED strip. And the purpose of this was actually to light up the interior of the cabin so that when it's kind of dark outside, we can still capture an image. And the interior lighting of the vehicle was not sufficient in order to do this. So using this particular setup, we would essentially turn on the camera and the light, and then we would capture the image, and then the Raspberry Pi would transmit the image through Wi-Fi into a remote server, and the remote server would actually have the prediction model, and it would display the results after executing it on a web page. So we decided to use a convolutional neural network in order to achieve this task. So this is the default architecture of a VGT16 convolutional neural network, and of course this network would be fine-tuned to suit our data set, and then finally the results would be validated using techniques such as confusion matrices and so on. And this was the actual setup inside the vehicle. So as you can see, the LED strip and the camera is actually overhead, just above the rear seating area, and the remaining part of the circuitry is in the trunk of the vehicle. So just some samples of the images we got from the vehicle. So as I mentioned earlier, there are 3 categories: empty, trash, and valuables. So it was essential that we initially collected a data set for training, and we collected just over 1,000 images. And of course, with image augmentation, it kind of doubles because we require different image augmentation techniques in order to augment this data for training purposes. And there was also other forms of variation. So there were shadows in the seats and the different lighting levels, and also the kind of open and closed states of the rear doors, as well as in some of these images, you can see the front seats are kind of visible as well in the image itself, the back part of the front seat. And this was the final confusion matrix of the prediction model. So we used the total test set of 140 images, and 12 were predicted wrong in the final results. And then we also used these kind of spreadsheets in order to actually get the specific certainty values for each of the categories for a single image. And it was very useful during the training process in order to identify certain patterns of false predictions. And a few more samples of empty images first. As you can see, the certainty is pretty high, and also some trash objects detected, and then also some valuables. So all these images were obtained during our demonstration last year, and also during the testing phase. And moving on to like some patterns of false predictions. So in this image, you can see that this mobile phone is actually not detected because of the glare it forms due to the shadow. And then over here, you can see that this unique case of unpredictability when the driver's seat is kind of pushed all the way back, so that you can see these knobs on the headrest. And this is actually not a very common scenario in driving, because the driver's seat would probably not be pushed all the way back. But then again, it was important to document that this was actually a pattern. And then here we can again see that the mobile phone is not detected due to a lack of contrast. And this is again a marginal misclassification where the trash can is actually detected to be a valuable. And again, it's due to the combined factors of the contrast as well as the object being a bit further from the camera. And the total cycle time to process a single image was between 5 and 17 seconds. So the main factor in actually having this big range was because of the image transfer time, which is the most crucial factor in this second bar that you can see. And this, of course, depends on the stability of the internet connection. And just to make a quick comparison with the previous studies, so this particular application in terms of crash detection is very unique, and there is a very unique data set as well. And also the convolutional neural network that I used was much simpler, and therefore it was a bit more easier to train, I would say. But perhaps if you use a deeper network, you could maybe increase the accuracy even further, and of course account for some limitations that we can see in this particular model. And also there were some cons, nevertheless, and these drawbacks were mainly because of the data itself. Because, for instance, in the trash category, we were only able to have like, as you saw in the images, there were only bottles and trash cans. So if this could also be expanded, it would then result in a much more reliable prediction model. And also, as a whole, there's a certain amount of bias in the data set due to practical difficulties in actually obtaining these images during the pandemic situation. Because for the training process, all of these images have to be obtained manually by placing the images in the vehicle and then actuating the camera. As an overall summary, so going back to the research question, we can see with the results that it is actually possible to implement this kind of application in real time. And of course, the accuracy does suffer to certain sources of randomness. And the best way to actually overcome these issues is to expand the data set and also integrate the system into an actual shared vehicle and then obtain more images to fine tune the model even better. And then in the process, we can also obtain more natural data because in this case, everything was done manually by placing objects in the vehicle and capturing the images. So integration of the camera module into an actual shared vehicle would definitely give a way to better results and implementation. So having said that, in our future scope of the studies, we hope to continue to develop the algorithms and also more importantly, to integrate this vision-based detection system to an odor detection model, which will also be inside the vehicle. And this odor detection model is currently being developed by our project partners in Spain. So we're actually a collaboration. And once the two systems are integrated, the integrated algorithm will produce a cleanliness level on a scale of 1 to 5. So with 1 being very clean and 5 being very dirty. So the purpose of doing this is actually to generate a corresponding action scenario, because based on the level of cleanliness, the type of maintenance would probably be different. So that is where the project is headed. And that's pretty much it for the work that I've done for my master's thesis. But if there are any questions, I welcome you to ask me. Thank you very much for your attention.
So Nilusha, we have 2 questions already in the Q&A. Could you navigate yourself there? And meanwhile, I can read it up. So what was the reason to choose CNN over other architectures?
Yeah, so basically the main benefit of using a CNN for this particular application is that the application with regard to the data set is very unique. And also, if you also want to know why I chose a VGG16, it was mainly because of its simplicity. Because like usually when you start to fine tune a convolutional neural network, it takes a lot of time, and the easiest way to is actually start simple. So for instance, if the VGG16 perhaps didn't give me good results, then I would perhaps move on to a deeper network such as the ResNet 18. But since it did give me like good results for this particular data set, and the preliminary accuracy values were also good, I decided to stick with that.
Yes,
So
and then we have a related question. Like, do you have to train this CNN model every single time you want to deploy it? And then where would you like to deploy it? So where would you like to start?
Oh yeah, so we already have plans for that as well. So basically, to answer the first part of your question, if you're actually using this particular prediction model to a different model of a vehicle, then you would definitely have to fine tune the network as well. But right now we are working on building a camera module that will be sent to the SEAT facilities in Spain, and so that it will actually be installed in this vehicle. And then we would sort of collaborate to get more images. And then we can actually compare it to the current model that we got from our research vehicle, and also the results we get from that particular concept car. So that is how we plan to deploy it immediately. And then based on those results, we will again test with another, perhaps different model of a vehicle, like an SUV, for instance.
Thank you so much for the excellent replies. We have 2 more questions in the chat, and you can still feed in. So Nilusha, could you reply them in the background? And I'm handing over to Heidi to introduce.
Yeah, for sure. I will reply to this question.
Thank you.
Yeah, thank you very much for your attention.
Thank you for the presentation. Our next presenter is Klaus Kivikas, telling us about simulator environment to test driving assistance solutions. In this presentation, This postdoc, Klaus, showcases the new simulator rig built for driver assistance development. Klaus will also discuss the Carla software, which is an open source software for autonomous driving, with a focus on the modifications needed to get the steering wheel and pedals working. Listen now as he shares findings and observations about the limitations of the vehicle physics used in Carla. Over to you, Klaus.
Hi, can you hear me?
Yes, we can hear and see you.
All right, I'll start sharing my screen. There, is it all good?
It's all good.
All right. Yeah, hi, I'm Klaus Kivekäs. I'm a postdoc from Aalto University, and I work in Professor Kari Tammi's research group. In this presentation, I will talk a little bit about the vehicle simulator rig that we have recently built and the software that we will use with it. So yeah, I will start off by showing some pictures of the rig, and then I'll move on to the software, which is Carla, which is a software package for autonomous driving simulation. And Carla runs on Unreal Engine, which I will then also discuss a little bit. And then after that, I will move on to describing what we have done to get the steering wheel working with this software. And in particular, the force feedback system in the wheel. The force feedback is the motor system in the steering wheel that generates torque in the wheel. And I also have a couple of demo videos of that in action. Okay, so here are some pictures. And as I said, we finished building this rig recently. We're still missing the monitor and the PC, so we haven't actually got to use it yet. Features some high-end equipment, like, for example, a SimuCube steering system, which is a direct drive steering system. So in this case, it means that the steering wheel is connected directly to the shaft of the electric motor, so there's no gearing in between. There's just a high power motor. And the purpose of this rig is so that we can develop driver assistance and autonomous driving algorithms. And then a little bit about Carla. So as I mentioned, it is a software package for autonomous driving simulation. And it is open source, so you can download it at carla.org free of charge. And there's all sorts of things that you can modify in the simulation. So there's many environments to choose from. You can modify the weather, the vehicles, pedestrians, what have you. And you can also add sensors to your vehicle and read them. So sensors like cameras or a GPS sensor, for example. And programming is mainly done in the Python language using their Python API. And in this API, you can set up the environment and vehicles and all that stuff. And you can also do your own control algorithm for your vehicle. And as I mentioned, Carla runs on Unreal Engine, which is a popular game engine. And it is also free to use. You can download it from the Epic Games launcher. And this engine also comes with the NVIDIA physics vehicle model, which Carla also then uses. Coding in Unreal Engine is done primarily in C++, but there's alternatively also this mode called Blueprints, which is sort of a graphical programming system, which you can see a picture of here. I think it is much more beginner friendly than just raw C++ coding. So for example, in this image, you can see these different blocks which perform some operations, and those blocks are connected with these lines, and the programming logic then sort of flows along those lines from one block to the next. It is a very intuitive system to use. So then about the steering wheel control. So Carla can read the angle of the wheel by default, but what it can't do natively is support the force feedback system. So we had to do some modifications to get that to work. And once we have that working, then we can use the steering system for driver assistance system and autonomous driving algorithm development, as well as also we can model the torque in the steering wheel. So as I'm sure you know, when you're driving a car, the steering wheel isn't just lifeless, there is torque coming through to it from the wheels. And so we could also model that. And to accomplish these things, we used the Logitech wheel plugin for Unreal Engine. And despite its name, it actually works with any wheel. And in terms of the driving assistance algorithms, the way we can control the wheel is that we first create a virtual controller in the Python script. And then Unreal Engine reads the position of the virtual joystick, and then it sends a torque command to the steering wheel based on that virtual joystick position. And then there's a demo video of all of this in action. So this was done with my home setup because, as I mentioned, the PC and the monitor are still missing from our office rig. And in this setup that I have, the steering wheel is a lot worse. It's a belt-driven wheel by Thrustmaster. So in this demo, the car tries to follow a GPS route, and the steering wheel is being controlled by the Python algorithm, which also controls the throttle and the brake. So there is nobody driving here or turning the steering wheel. It's all happening on its own. And to explain briefly how this control system works, basically the system looks at where the next GPS target point is and how badly the car is pointing away from that target point. And then the control system adjusts the steering wheel angle so that we will get the car to point in the correct direction. Now, this isn't necessarily very realistic because in the real world we couldn't just rely on GPS data to navigate. But the purpose of this demo is to more just like show what kind of things can be done with a simulator setup like this. So then I'll start the video. So as I mentioned, the car is driving autonomously here, and so it's operating on its own. Also, the throttle and brake are being controlled by the Python algorithm. So first, we take a roundabout here, and then we get out of it soon, and then the algorithm will notice that there's a car ahead, so it will try to keep a safe distance to that. And then we approach an intersection where there's red lights, and the car ahead of us stops at the light, so we also have to stop. There, and then we'll be stationary for a little bit. So something I want to mention is you may have noticed that the wheel is a little bit shaky. So even here when we are stationary, it's like moving about a little bit. And I think this is partially because the control algorithm isn't necessarily that well tuned, but it also has to do with the wheel because it's nowhere near as good as the one that we have in our office rig. So this wheel here, it just has this like low power motor with belt transmission. So there's also like a lot of internal resistance inside the wheel. And all of that amounts to basically the wheel being quite a bit harder to control precisely compared to the one that we have in our office. And then as for the next video, as I mentioned earlier, we have also tried to model the torque that you should feel in the steering wheel. And that modeling has been done based on the tire forces and slips. And it has been done in Unreal Engine because that's where the vehicle model is. And so in this video, I will swing the wheel and then I'll let go of it and just let it do its own thing to see if it reacts as it should. And as you can see, when I allow it to rotate freely, it will behave pretty much as it should. So there I let go of it, and then it sort of swings about. Yeah, and that's the video. Oops. Yeah, so as a summary, I talked about the simulator rig that we have built and the software that we use with it, namely Carla and Unreal Engine. And I showed a couple of demos. In the first one, the car was driving autonomously. And in the second one, I showed the torque modeling that we have done for the steering wheel. And one more thing to mention is that the software should also work with virtual reality headsets, because Unreal Engine has native support for them. And we have recently received the Vario headset, which is a high-resolution VR headset in our research group. So we will also be able to use that in our research, which will be very interesting. But that's all for this presentation. And if you have any questions, feel free to ask.
Thank you, Klaus. Now we received one question to the Q&A. So how accurate the physics of the car? How many degrees of freedom does the vehicle have? Is it a track model or more complicated?
I guess by track model you mean the bicycle model. So it's not that, it's a four-wheel model. I initially was intending to talk a little bit about the limitations of the model here, but had to cut that out because of time constraints. But I think one of the main limitations of the model is the tire model, which is quite simplistic. So if you're familiar with vehicle dynamics, you will know that, for example, when the slip grows, at some point the tire force should reach its peak, and then when the slip grows after that, or increases after that, the tire force should actually reduce. But in the physics model, that doesn't actually happen. The tire force stays the same after the peak, which makes a car quite a bit easier to control than it would be in the real world. But it should be possible to make your own tire model if you so choose, so you can improve that aspect of it.
Yes, and if you navigate to the Q&A window, we have 3 more questions. I'm just picking one, and then we continue with the next speaker. So have you considered to use the Stuart Gough's platform as the base ring?
Stuart Gough platform as the... I don't know what that is, I'm afraid.
Okay, so then offline you could consult and you could get a few good ideas, quite likely. Do you do multidisciplinary research? So do you collaborate with other departments? For instance, you mentioned this Vario headset.
So far, no, but I think that would be something very interesting to do now that we have these tools available for us.
Yes,
but, so far we
related to virtual and mixed reality, we have lots of research also in School of Science. Yeah. And then in the School of Arts and Design. So those collaborations you could check out. But thank you so much. I'm handing over to Heidi to introduce the next, or the break, right?
That's exactly right. We're going to take a break. We're going to take a 10-minute break or until about 13:10. So please sit back and watch this Career Design Lab video. Get up and stretch, and we'll see you back here in about 10 minutes. Thanks.
How to find your purpose in life. 1. Create your calling. Don't wait for it. Do you want your work to be a job, a career, or a calling? Most of us would prefer having a calling. Calling is not something we're born with, but something we humans as meaning makers create. Let curiosity guide you. Feel, don't just think. You can spend hours, days, and years trying to figure out what the meaning of life is. To get a sense of which purpose resonates with you, listen to your intuition while working. Do I enjoy this? Does this inspire me? Pause for a minute and let your life speak for itself. 2. Transcend yourself. There are millions of purposes to be found, causes to serve, and problems to be solved in communities and organizations worldwide. Where are you needed the most? Get out there and explore. 3. Experiment. Don't overanalyze. How could you know if something's a fit for you if you haven't tried it out? You can start the experimenting already as a student by getting involved with different activities and fields of study. Each experiment will teach you something new about the world and yourself. Your purpose will reveal itself.
Hello, everybody, and welcome back. I'm just going to give you a second to have a seat. Thank you for joining us today at the Mechatronics Circus at Aalto. Welcome to the parallel session, Sustainable and Digital Rotating Machines, demonstrating 5 different research projects. Raina Viitala will start us off. Raina, would you like to go ahead and get started?
Yeah, so thank you, Heidi.
We can hear and see you.
Yes, good. I was just about to ask you to confirm that you can hear me and see me properly. So,
Great.
Is it now time to start the presentation?
I was going to introduce you and say
All
that
right.
you're the youngest professor of the Mechatronics Research Group. You have a solid background in experimental research of large rotating machinery. Raina is the head of the Aalto University Rotor Laboratory, ARotor, for which he gives us a short glimpse here. After Raina, the researchers from the ARotor Laboratory will showcase their latest findings. Over to you.
All right, thanks, Heidi. Let me share my screen and let's check that everything works, and then I'll keep going.
We can see your desktop. And we see the presentation.
All right, so I assume that everything works fine now. So, well, yeah, welcome to the Aalto University Rotor Laboratory. I was going to give you a short streaming from our laboratory and introduce you to some but due to current reasons, I now have to stick to this kind of slideshow as well as many other presentations today. So, rotating machinery. Why should I care? So, what is the impact of rotating machinery and meaning of it? Well, I can say that nearly all the generated electric energy produced in the world is generated by large rotating machinery. Of course, there are things such as photovoltaics and such, which create some proportion of it, but most of the energy is indeed produced by large rotating machinery. Rotating machinery is also responsible for half of the global and 2/3 of the industrial energy consumption. So we are also quite big on the consumption side, so to say. What does all this mean? It means that even if we achieve incremental improvements, that signifies globally vast energy and material savings. And especially these energy savings are demanded by EU Green Deal and, for example, these United Nations Sustainable Development Goals. And in our laboratory, in Aalto University Rotor Laboratory, we have chosen to use and exploit these new and newest ICT methods such as artificial intelligence, machine learning, and such. And with those, we have the possibility to achieve also major breakthroughs. And that will have a major impact on climate change and sustainable society. The impact we are creating it together with our industrial partners, and of course not alone. And you can see some of them stated here. Most of the projects that we are collaborating with right now are presented during this session, and also in the earlier session A, there was a collaboration with Kongsberg. All right, then about the laboratory. So Aalto University Rotor Laboratory is a full-scale rotor laboratory. We can go to industrial rotor sizes up to 25,000 kilograms, which is unforeseen in any university laboratory in the world. Our goal and this kind of slogan is manufacturing for operating conditions. So we are not focusing only to manufacture and do and design rotors so that they would behave well in the laboratory conditions, but so that they would actually behave well in the actual operating conditions where they are brought. So be that a windmill a couple of 100 meters up in the sky, is that a marine propulsion system in a ship, or is it a paper mill in a Finnish paper mill city? So we do that by doing static dynamic geometry measurement. We do rotor dynamics in lateral and torsion directions. We investigate bearing excitations, which is also actually my background. We are able to investigate foundation stiffness effects on vibration, and because we are talking about large rotating machinery here, we are interested particularly in harmonic and subcritical vibrations. And for this digital twin machine learning, artificial intelligence analysis that we do, we are able to do full-scale verification. So not only to test things with simulation models, but to test them to actually verify that it works in full-scale industrial sizes. Okay, I was so sorry that I could not stream any live video from our laboratory, so I decided to take an old video. I hope that you can see it, but this is one of our research projects that I have actually been involved in heavily. So here we are actually 3D grinding a rotor shaft to improve its bearing geometry in a way that it actually minimizes the lateral vibration resonances that normally occur due to the excitations coming from the bearing geometry. And this is one of the many research devices and ways and full-scale setups that we can use to achieve our mission. All right, let me just give you a short, how does this go to the next slide? Yeah, let me just give you a short overview of the session that we're talking here. So the researcher from my group, from the ARotor group, will next present highlight some of the research projects that we have ongoing right now. Of course, they are all conducted together with our precious and active industrial partners, which are stated on the right-hand side. So the first one will be a team which investigated a digital twin of powertrain. We have that project together with ABB, and in that presentation you will see how to straightforward model electric powertrains in so-called openTorsion platform. Interesting things coming. The next topic will be, after that, some frictionless motion. So how to achieve frictionless motion. That sounds unbelievable, but Mikael and Valtteri will show you how that's possible. After that, there is a study focused on eddy current-based runout problems. So eddy current-based condition monitoring is the de facto standard in many industries, such as process industry, to condition monitor electric motors and pumps, for example. There are some problems related to eddy current-based condition monitoring, and Tuomas shows how to tackle those. And finally, Sampsa will give a short presentation on how to identify problematic rotors in cardboard and steel industry, because as we know, there are multiple, even 100 rolls in a single cardboard machine, and how to find out which one is the one that should be maintained the most carefully. So Sampsa shows how to do that. Okay, but without further ado, I would be ready to jump onto the first presentation by Sampo, Risto, and Urho. Heidi, feel free to move this forward.
Thank you for the introduction to the session. Do we have any questions? If there are any questions, you can put them in the Q&A. We still have a little bit of time before the first presentation, but we can also get started if Sampo is ready.
Yeah, the Q&A is empty, so we could continue.
Great.
Yeah, let's go to the questions when there's actual content coming.
Great. And if you get questions, Raina, you could also respond with text. So that's no
Yeah.
problem as well. Super.
Thank you, Heidi.
You bet. Thank you for the overview. Our next presentation is Digital Twin of Powertrain, straightforward modeling of electric powertrains and openTorsion platform. Sampo Laina is working on his master's thesis, concentrating on toroidal vibrations in electrical powertrains. In addition to Sampo, Urho Hakkonen and Risto Viitala are involved in the project. Urho is a third-year mechanical engineering student, and Risto is a doctoral student in the same program.
Thanks for the introduction, Sampo here.
Are you ready to go?
I'm ready to go.
Awesome. Go ahead and bring up your presentation.
Let's put on the camera too.
Thanks. And if you would also go to presenter mode.
Just a second.
Of course.
Okay, here I am.
I can see and hear you. Great.
Let's move to the start. So the topic of today's presentation is the digital twin of powertrain, which is the sort of a larger scale project that is going on at the ARotor laboratory, focused on the digitalization of these rotor systems. And today I'm going to tell you a little bit about my master's thesis topic, which is the torsional vibration of electric powertrains. And because it's a sort of a larger topic to cover, I'm focusing today on the openTorsion platform, which is basically a side product of my master's thesis. And so my name is Sampo, and also Urho and Risto have been preparing this presentation with me, but I'm presenting alone today. So the motivation for my study is that, or our study, should I say, is that the amount of electric drives is constantly increasing. Like Brian said in the previous presentation, that most of the world's electricity is produced by the electric machines, and it's almost all of it is produced by rotating machines and consumed. Most of it is consumed by rotating machines also. I don't know how it was, but whatever. It's clear to me that in the more sustainable future, we are focusing more and more on electric motor-based drives, and use of electric energy is only increasing. And a closely related topic to the use of electrical powertrains is that whenever there's a variable speed drive, so that the electric motor is driven with variable speeds, then it's often required to analyze the torsional vibrations. So this torsional vibration is the vibration that occurs by the twisting of the axis or axles in the powertrain. And modeling and analyzing this torsional vibration is extremely important, so that we can ensure that the powertrain is operating and functioning reliably, and it doesn't have major problems such as braking in middle of use. And also we want to analyze the torsional vibration so that we can prevent delays during the construction of the powertrain or possible brand damages for the companies that are involved in building the powertrains. And also we want to prevent the early service so that we don't need to fix anything prematurely. And what's unique in the torsional vibration modeling is that we require the model of the entire powertrain. So you can imagine that you are driving a car, and when you feel that the steering wheel is shaking, you know that it comes all the way from the tires. So that's torsional vibration. Basically, you can feel the tires in your steering wheel, and it comes all the way through the powertrain, the vibration. And every component of the powertrain is contributing to the torsional vibration. So it's really important to model it with a holistic approach, so that you get the whole model of the powertrain. And when it comes to electric motors, there have been some really smart guys researching this topic before me. For example, at ABB and VTT and the School of Electronics, and they have come up with these highly portable models for electric motors, and or should I say electric machines in general, so generators and different types of electric motors, which can be used in a completely new way in the torsional vibration analysis. So what we are proposing here is that to create this sort of a ecosystem of digital twins. So in short, we have the companies that are generating these parametric models of their products. So this could be the coupling manufacturer or electric motor manufacturer, and they usually have very sophisticated models of their products, basically. But it's not very smart to share your best models with your competitors. So what we really need here is a digital twin interface, so that we can share the important parts of the more complicated models with the users who are building powertrains. So we make these abstracted digital representations of the more complicated models through methods of model reduction and such, and then those can be distributed through web-based interfaces, so web-based application programming interfaces. And this is where our topic comes in handy, so that we have noticed that there is really a lack of open source platform for torsional vibration modeling. So there are some really great modeling tools modeling tools and programs that are proprietary software for building these torsional vibration models. But now, during my master's thesis research, I have been coding this Python library, openTorsion, which can be used to also used to build these torsional vibration models. And now together with the industrial partners, we are looking for ways to use the new types of digital twin models and incorporate those in the torsional vibration analysis. And now in our ARotor laboratory, we have once in a lifetime or only one of a kind in the world possibility to model these powertrains. So validate our not only model but also to test these models in practice. So this new setup that we have had great help from ABB and all of the researchers before me, basically, who have been building this amazing test setup that we have at the ARotor Lab. We can use this to verify the models that we create in these projects. And this setup is highly versatile, and we can simulate different operating conditions and setups. And we'll look a little bit closer to this here. So what we currently have in the lab is a paper machine roll, which is labeled as a rotor here. So this big thing in the middle. And we have the possibility of applying lateral force with this belt to the rotor. And then also we have these foundational stiffness varying devices, so we can modify how easily it can shake in the sideways direction while it spins. And then we have these couplings here and torque sensors that connect these 3 different motors to the paper machine roll. And we have a synchronous reluctance motor on the other end, and then we have another synchronous reluctance motor, and then we have an induction motor, and the induction motor can be swapped with the reluctance motor to test out different electric machine models. And Now, as you see, the motors run in opposite directions. So one motor produces the spinning velocity or rotational speed, and other motor is used to generate different load conditions. And all of these motors are run with variable speed drives. And we also have a research variable speed drive device, which can be used to test out these different algorithms for driving the motors, which is not possible with normal stock variable speed drives. And here we have great help from it's the School of Electrical Engineering when we need it, because this is difficult for us always as mechanics. But now, without further ado, I'm going to present now how we have built basically this React web user interface to basically show you how we can use the openTorsion package. So I'll show you this video of how we can build a model of this laboratory setup very conveniently using this web user interface that on the back end uses the openTorsion Python library. And it should be playing now. So let me know if it doesn't work. And so we add the role to the model, and then we add the two couplings with this drag and drop feature, and then the induction motor on the other end, and then the synchronous reluctance motor, which is the loading device, which is added on the other end. And then we have the gear that connects those two. Then we can calculate the free response, so the natural torsional frequencies of the system, and plot this Campbell diagram, which is used in torsional vibration analysis to compare the driving speeds and the natural frequencies. And now with this interface, it's really easy to swap out. So say you want two paper machine rolls, it's possible just to drag and drop them in. And this really highlights the difference when in traditional software, this kind of modification is not possible because you are not able to use the code directly in proprietary software. And then we get a little bit different results when we had a little bit altered drivetrain. And then that's about it. And I also had this backup image of the interface in case the video breaks up.
The video worked just great.
Okay, that's great. So then we can move on to the conclusions. The openTorsion platform enables the simple creation of these holistic powertrain models. And by holistic, I mean that not only we consider the mechanics of the powertrain, but we also consider the electrical effects and different kinds. And in the future, we have many plans to make this even better by adding fluid flow effects and various damping effects and such. So now that we have built this great platform, I'm really excited to see what the future brings in the coming years. With the great lab and with the great software, we can really accomplish great things. And we chose to do this as an open source software. So I'll be publishing the openTorsion soon when I wrap up my master's thesis, and then it will be available to everyone. And we hope that we can get collaboration on it with different universities and such, and the industry, of course, to see basically if we are able to make this a real thing that is used in the world and not only on the research table. So thanks a lot. This is my presentation. If you have any questions, please post them in the Q&A.
No questions at the moment in the Q&A, but we don't let you to run so fast, Sampo. So I have a question for you. So this 8 rotor platform. So how long does it take, for instance, to build gear 3, a new element to the software? How does it work? Who is developing it? Who is implementing it?
So you mean like now
So you had rotors and gears, number 1 and 2 and 3, and you visualized it, and then you have these elements, and you are just pulling in the elements, and then you get these auto simulations. So how long does it take for you to build an extra element there?
Yeah, 100%. I understand the question. So this is really the main thing that we are trying to solve here. So what is the interface between the company that provides the model and the user? Certainly, it's going to be a lot easier if the component manufacturer can provide this digital twin of the product. So for example, say you have a big electric motor manufacturer such as ABB, and they are able to make this digital twin of their motor, and I can simply import it through this web user interface to my modeling software. Then it wouldn't have for the user, it wouldn't require any work. It would be just like a snap of my finger, and I have modeled this very great model of an electric motor. So that really is the goal. If I were to make it manually, then of course it's a lot more work. But the openTorsion is more about integrating the models than creating them.
And what is your experiments? What is the reliability of those models that you get from industry? So how many mistakes you have to correct, or how you validate the model?
Yeah, well, this is the great thing about ARotor, that we have this massive laboratory which has all these different kinds of parameters that we can vary so that we can validate the models in all sorts of conditions, and we can swap out the motors and test different cases.
Yes,
so,
and finally we got a question. So what could be the format for transmitting the digital twins of products to enable efficient model exchange? It's in the chat window, not in the Q&A.
Yeah, so for transmitting the models, well, it could be some sort of table-based XML format, or it could be there are some large-scale projects revolving around this dynamic model sharing, such as the feature mockup interface, FMI, and yeah, it really the basically industry standard for sharing part models for the moment is the step file type, which is based on this XML format. But really, it could be a text file for now. But I mean, I don't know. That's a really nice question, and that would be when the perfect solution is solved, then everyone will use it, I hope. But I don't have a clear answer. I have some ideas. It could be a XML format, or JSON. JSON is the format of the HTTP web at the moment, but I don't have a clear answer to that yet. I hope I will by the time I finish my master's degree.
Thank you, Sampo. We are handing over to Heidi.
Yeah, thank you.
Thank you, Sampo. And your other teammates owe you for giving the whole presentation, so be sure to remind them.
No, they don't owe me anything. I owe them.
Excellent teamwork. Our next presentation is frictionless motion, aerostatic bearings. This is being presented by Mikael Miettinen and Valtteri Vainio. Mikael is a doctoral candidate in mechanical engineering at Aalto. He and Valtteri will introduce the concept of gas lubricated bearings and how they are applied in the research on large rotors. Valtteri is pursuing his master's thesis. Over to you guys.
Yes, thank you.
Hey, we can see and hear you just fine, Mikael.
Yep. And can you hear Valtteri also?
Here I am.
Yes, and we can see him. Hi.
Yeah, great.
And now you should see my slides also.
Yes, everything looks great.
Great. So we are going to tell about frictionless motion and air bearings. This sounds quite interesting, that how it can be frictionless. So we have something moving at speed, and then there is very close to zero friction because they will not actually touch each other but float on air. And first we are going to show you a video. So this blue thing under the big weight is an air bearing, and as you can see, when you turn on the air supply, it moves quite effortlessly on top of the steel disc, and you can push it around with just a finger. And when you turn off the air, the movement stops because of the air bearing stops working. So now that you have seen this in action, we can go a bit deeper on how does it actually work. So these air bearings, they are non-contact bearings. So that means that there is an air film between the bearing and the opposing surface that carries the load. And these allow very high accuracy in the motion because of the all miniature errors in the surfaces do not affect the result because the air film averages those errors. And in these pictures on the right hand side, these with bearings, they are porous bearings. So they have a porous material that the air goes through. And in the center bottom, there are those two bearings that use orifices to feed the air. But we are focusing only on these porous bearings because they have some benefits for us. So how does that actually work? So these porous bearings, they have this porous material that the air flows through. So the air supply that is coming from the external source, so a compressor, for example, it is fed with the pneumatic line inside the bearing housing and is distributed behind the porous material with these supply grooves. And from there, it seeps through the porous material into the air gap, and it pressurizes the air gap. And the air is slowly escaping from the air gap, and the fact that the air gap is so small restricts the flow and allows the high pressure to build up. So here we have, on the bottom, we have two images of the bearing. So on the left, we have this normal size image, and the diameter of the bearing is 40 millimeters in here. And we can see that the surface is quite shiny, but it has some small things there. And when we look at that with microscope, we can see on the right hand side that there is actually these miniature pores in the material. So those pores are the ones that the air flows through. And the scale of this thing is quite small. So the big diameter in there, it's the human hair. So that is roughly 50 micrometers in diameter. But typically the bearing gap is only 5 to 20 micrometers high. And the tolerance for the bearing is just 1/10 of the bearing gap. So in half micrometer to 2 micrometers. So this requires quite good accuracy to manufacture. So now that you have seen a little bit of the principles behind the air bearings, we can look at this video again. So at the bottom, we see airflow on the red number, and then we can see the pressure in the dial when we turn it on from the background. So now we turn the air on, and the air rushes through the bearing and pressurizes the bearing gap and lifts the weight that is 10 kilograms here of the steel disc. And we can move it around very easily. And now when we turn off the air, the air film escapes and the bearing drops down back onto the steel disc. And next, Valtteri will tell us how we are using this in our current research.
Yeah, thank you, Mikael. So on my master thesis, I'm making research of robust air bearings. So in common and previous research, all air bearing research has concentrated on to make a perfect air bearing which has the best possible vibration damping and highest possible load carrying capacity. And all previous research has concentrated on those details, how the bearing needs to be manufactured to reach those so-called perfect targets. And because we are targeting the robust air bearings, it's not necessarily the perfect bearing in all use cases. So we call our bearing all-terrain bearing, which has such properties that they are optimal in its designed use location. We are making empirical investigation with 27 different combinations of all kind of input parameters needed to manufacture the air bearing. So we are varying porosity and manufacturing methods to make those 27 different test units. And with those test units and with known input parameters, we know after tests how those input parameters has affected on the bearing properties. And with that information, we are targeting to gather knowledge about how all input parameters affect on output parameters of the bearing. And Mikael will present next his master thesis and research equipment there, where it's really all-terrain bearing used, and it's not even near of perfect air bearing.
Yes, so here we can see a short video of the air bearing or the robust air bearing in action. So this large spinning disc here, it's the same disc that the air bearing was floating on in the previous demonstration, and this rectangle here is the air bearing. So, and there is a 1 millimeter of axial runout on the face, and the air bearing is acting against it with no problem. And how this is actually possible when we know that there is the few micrometer high gap between the air bearing and the opposing surface. So in addition to the materials and the manufacturing methods, we are also looking at the better design for these operation conditions. So we are actually using a bearing with the center removed. So just like on the right-hand side here, that we have this empty volume and then just two small pieces of the porous material, graphite in this case, and the air bearing is hung on these flexures that allow movement of the bearing face, and this allows that the bearing follows the opposing surface more easily. However, the volume in the middle is also pressurized to the same pressure as the bearing gap. So in sense, this bearing gets the same load capacity as this typical bearing on the left that has this full face and big area, but it gives a trade-off in stiffness because of this large volume here acts as a spring, and there is these springs behind the bearing pads. So that is a trade-off, but in these operation conditions, it's a good trade-off to make. So this is tested with this high runout shown in this video, and we can look at it again, and we can see on the right hand side the internal structure. So this is the air bearing graphite going around, and then this chamber volume in the middle, and then we see the flexures that hold it in place. And this allowed for this large runout on the surface. So in conclusion, we are developing these robust air bearings or all-terrain bearings. And the real key interesting thing is that because of the almost frictionless nature of the movement, we can improve the energy efficiency of systems by reducing friction. So this is just like a mechanical product, a simple one that can improve the efficiency. For example, in cardboard manufacturing, there are potential applications in replacing these oil lubricated parts by these air lubricated bearings. Thank you, everyone, and let's see the questions now.
So I myself have the first question for you. So what are the most vulnerable parts of these kind of systems? So
let us go back to this image. So it's usually this bearing face. So this is usually the softest part in the system. So this gets damaged from contact to the opposing surface. So if the air film is not enough to carry the load, then they will rub together, and then there is of course damage from the contact.
So what is the lifetime of this kind of device?
With proper design and proper design for the operation condition, we can achieve almost infinite life because of there is no contact.
Yeah, assuming that we are not occurring any incidents or accidents with the bearings.
Yes.
So the next question is also related to this. So what happens to the graphite if the air supply fails and there is contact?
Well, the graphite is one reason that we use the graphite is that it is like a lubricant material itself. So the friction coefficient between graphite and steel is really low already. So there will be some small like rubbing. So as you can see from on the right hand side, there you can see some small arcs on the bearing face that have come from contact during the test use, but it is quite tolerant to the damage.
Great. And one more question. Are the most difficult challenges in the material domain or in the manufacturing domain when it comes to the air bearings?
Well, it is kind of like a coupled problem because of the material properties affect the behavior of these air bearings because they are quite dynamic system in sense that it is the vibrations can affect the air film quite easily, and the vibration properties come from the material properties of the restrictors that we use, and to add to that also the geometrical properties. So how flat we make the face has quite significant effect on how it works.
Thank you so much, Mikael. Thank you so much, Valtteri. I'm handing back to Heidi.
Thank you.
Thank you. If there are further questions for our presenters, you can always use the Q&A and they can get back to you by text. Our next presenter is Tuomas Tiainen, presenting electrical runout and eddy current based, an eddy current based rotor condition monitoring. Thanks for your patience. Tuomas received his Doctor of Science degree from Aalto University in late 2020. The subject of his thesis is the multi-probe roundness measurement. He now continues further research on metrology and paper machines as a postdoctoral researcher in the Department of Mechanical Engineering. Today, his presentation focuses on runout measurement and electrical machines. So over to you, Tuomas.
Oh, yes, thank you. Nice to see that we have over 30 people in the audience. Now just let me share my screen. Can you hear me?
I can hear you just fine. I'll give you a yes, it's all go once you have your presentation up.
Yes. Oh, all right. Yeah, now I'm overriding your sharing. Is it all right now?
It's great. We can see your pointer too.
Okay, great. So yes, today we're going to talk about eddy current-based runout measurement and condition monitoring in electrical machines. And this is an industrial problem which we initially started to work on with ABB, which is a large manufacturer of electrical machines, generators, motors, and the drives to use this equipment. And in 2020 September, we got funding from EU in a project called MetaWind, where we focus on metrology of wind energy systems. And that's the project now we're continuing this research on. And we're going to cover shortly some background, and then I'll describe the measurement setup and some preliminary results we have obtained already. Okay, in this picture, on the left, you can see a wind turbine. And on the right, I have put up two pictures of electrical motors. And as you know, these are the completed products. Inside, we have the stator and the rotor. The rotor is the rotating part, and the electrical energy to mechanical energy conversion is done in interaction by the magnetic fields between the stator and the rotor in an electrical motor. So in essence, an electrical motor and generator operate with the same principle. Well, before these machines can be taken into use, they have to be manufactured, and they have to pass a factory acceptance test. And a part of this factory acceptance testing is slow roll runout tests, which we're going to focus on today. So the actual problem is that when the manufacturers of these electrical motors assemble the machine, sometimes they notice that there is an excessive runout measured from the rotor. And in the worst case, they have to scrap the rotor if they cannot fix it at that time. So what does runout measurement actually mean? In several IEC, API, and ISO standards, these are international organizations which publish standards on these electrical machines. It's defined that you need to have this runout measurement. And runout is measured from a rotating body with a displacement sensor. So on the left here, we have a schematic picture. This is from the IEC standard. So as you can see, we have two displacement sensors in 90-degree angle relative to each other, which are used to measure displacement, while the shaft, which is here in a cross-hatched cross-section, rotates. So as you can imagine, this can be a little bit problematic. We are actually interested in the movement of the shaft. We want to prevent excessive vibration with this measurement and this verification. And even if the shaft remains stationary, but there is a roundness error to this shaft, we will observe a runout in these two probes.
Additionally, several standards specifically require eddy current probes. And we'll cover why that also is a bit problematic in a bit. So here, it's a bit technical, but don't worry, I will just read the most significant bits and explain it. So it says that you need to measure with these eddy current probes. These areas shall not be metallized, sleeved, or plated, and the combined total electrical and mechanical runout should not exceed the following. And the following is 25% of the allowed unfiltered peak-to-peak vibration amplitude, which in this case means 12.5 micrometers for a normal shaft of an electric motor. And as Mikael in the previous presentation described, the thickness of the human hair is 50 micrometers. So we're working with a very, very small tolerance here. So just to recap, the runout measured, the peak-to-peak value when the shaft rotates, measured with these probes, must not exceed 12.5 micrometers. All right, it's measured with these eddy current probes. An eddy current probe, here on the left is a schematic picture of how an eddy current probe works. There are several other options to construct this probe, but here we see a 2-coil eddy current probe. So in the upper coil, we input current, an alternating current with a high frequency. Then from another coil, we measure the voltage from another coil, and based on that, we can determine how far the sensor is from the conductive target we're measuring, because the alternating current in the upper coil causes eddy currents in the target surface. And this means that the displacement value, if you measure a different location where you have a different surface roughness, you have different resistivity, different electrical properties, different magnetic properties, you might get an error, even if the displacement remains the same, but the electrical properties of the position you're measuring changes, you might get an error. And this error is called electrical runout. It's the eddy current probe error due to inhomogeneities in the material. Okay, and how we go forward with this? We measure both with tactile probes and with eddy current probes. Here on the left, we have a diagram, schematic diagram, and here on the right, we have the actual measurement setup. So we have used 4 tactile, very accurate Heidenhain MT12 probes. And we used this with a multi-probe roundness measurement method, which we can then use to calculate the roundness error. And further, we can use it to compare it with the values given by the eddy current probes to determine the electrical runout, which in effect is the error of the eddy current probe. And here we have some preliminary results from one shaft we measured. So if I explain this here in blue, we have the runout measured with an eddy current probe. So as you see here, we have a large spike. Again, here we have some spikes, and again, here we have some spikes. In orange, we have the actual tactile runout. This is the true runout measured with a contacting probe. And additionally, we use the information from the second, third, and fourth probe to separate the roundness error from this measured displacement value. And this, in effect, is a breakdown of the components measured with the eddy current probe. So as you can see, some part of the eddy current probe reading consists of errors. One error is the electrical runout, marked in red, and one error is the roundness profile, marked in purple. In this case, the roundness error is very small. It's something like 1.3 micrometers peak to peak. But you can imagine if the roundness profile error was 10 micrometers, which is possible if you're machining a flexible shaft, you would also see spikes here caused by the roundness profile. So maybe to summarize this measurement, this is maybe just one case of measurement. And the main point here is that we have been developing a method where if you have a shaft, you can use this method to quantify. We have a tolerance zone of 12.5 micrometers. And with this measurement method, we can see which part of this tolerance zone is consumed by the electrical runout and the roundness error, and which is actual shaft displacement. So with this measurement method, if we have a problematic shaft, we can use it to determine what's causing the excessive runout. And this can be used to target the repairing operations in manufacturing of these electrical motor shafts. I'm working on a journal article on this subject. If you're interested, I'm very happy to tell more about it. Please send me an email. I can also send you the preprint of the article. Thank you very much. I believe now we have time for some questions.
So I have a question related to your algorithm. So do you have it in open source or you still keep it for yourself?
Yes, I did my doctoral thesis on this multi-probe roundness measurement. And I have published the algorithm, actually several algorithms on how to apply this separation of the roundness profile and the center point movement from multi-probe displacement measurements. If you're interested, I can send you a link, but I think you can, if you search my researcher profile, there's in my article concerning this uncertainty of multi-probe roundness measurement, there's a link to the open source version of these algorithms.
Yes. So do you do also laboratory measurements as contract research for industry for this kind of purposes?
Yes, we started this research as a contract research together with ABB. So yes, sometimes we do that.
Excellent. And then you mentioned like you use it for repairing operations, but I guess also you use it in product development, right?
Yes, actually we're working on some further research which we could solve the problem of the electrical runout, let's say with heat treatment or by modifying the surface roughness. So yes, we are also looking how to improve this situation. Now we have more looked on how to pinpoint what's the problem. And yes, certainly you could use this information in product development. The designers, when they specify tolerances, and even on a higher level, why do the standards give such a tight limit for this value? This might be a method of disseminating this information to the people who, the committees who make the standards, so they should maybe be a bit more relaxed in these standards. That's our gut feeling at the moment. And we're maybe hoping that these standards would not require specifically eddy current probes. And there's no explanation why these areas shall not be metallized, sleeved, or plated. So the standards, in my opinion, are a bit overtight. So yes, this has a direct connection to the design of these machines also.
Yes, and Thomas, your final question, what kind of methods there are to mitigate the eddy current probe issue in industry?
Well, the most obvious method is to not use an eddy current probe, to use some other displacement probe technology which is not sensitive to these types of errors. But we are now looking into heat treatment options. Maybe if we can obtain a microstructure in the surface of the eddy current probe, which is very uniform, maybe that could reduce the electrical runout. But I think we will leave that for next year's presentation. when we have some more information. This is something that I'm not aware has been researched before, so it's very interesting.
Thank you, Tuomas. Back to Heidi.
Thank you very much.
Yeah, thanks. Our next presentation is identifying problematic rotors from cardboard and steel quality data from Samsa Lehtiniemi. Samsa is doing his master's thesis starting at the beginning of this year. The thesis is part of the Artificial Intelligence Optimization of Rotating Machinery Governed Production Lines, for which he can tell you more about the project, which is about optimizing production lines deploying rotating machinery. It includes lines for producing paper, cardboard, and steel. In these processes, multiple rotors manipulate and form the end product. In Samsa's thesis, he is developing an algorithm that automatically identifies each rotor's contribution to the thickness variation of the end product using only measured thickness data. He can tell you more. Over to you, Samsa.
Right, thank you. Can you hear me well? Can you see me?
Yes, we can hear and see you well. Please bring up your
Excellent.
presentation.
All right, now you should be able to see my presentation.
Looks good.
All right, so like Heidi said, this project is about optimizing the production lines of cardboard and steel, and also paper and plastic film, but my focus is on cardboard and steel. And here you can see on the right a steel rolling line, a picture from a steel rolling line, and on the left you can see, well, actually that's a paper machine, but let's not tell anyone. And what's common to all these processes is that the end product is kind of squeezed between rolling rotors. So why are we doing this? What's the point? So first of all, each time you buy something online, it gets delivered to you in a cardboard box. So that's why we need a lot of cardboard now and even more in the future. And as for the steel industry, it produces a huge amount of carbon emissions. As an example, I can tell that there's one steel factory in Finland that produces 7% of all the carbon that the country produces, so quite a lot. So that's why even little improvement in these processes is good. All right, so there can be up to dozens, even hundreds of rolls in one cardboard machine or steel rolling line, like these 4 that you can see here. And each of these rolls has defects that cause imperfection to the end product. So imperfections such as these pits that you can see here. So we wish to know which roll causes the most imperfection, or more generally, which imperfections are caused by which roll, so that if we desire to have a better quality product, we could repair that roll, the one that causes most imperfections. But on-site measurement of these rolls is very difficult and expensive, so that's kind of out of the option. So could this be deduced from only the measured thickness of measured thickness variation of the end product? So could we identify these rotors only by measuring the end product? So the proposed method for doing this, and first I'll explain a little bit about the imperfections of the rotors themselves. So all the rotors or rolls have roundness errors that are repeated 1, 2, 3, however many times per revolution. And here you can see on the left one time per revolution error, and that's eccentricity. And then there is 2 times per revolution error, that's ellipticity. Then 3 times per revolution, that's triangularity. And so all possible errors that there can be on a roll or rotor can be expressed as a sum of these errors that are repeated a certain times per revolution. So here on the rightmost roll here has ellipticity and little bit of 5-lobe shape. All right. So then we would a good method would be to obtain the spectrum of the thickness measurement data and then identify the harmonic series therein. So here we have the spectrum, and here we have identified two harmonic series, one with green with 3 components and one in red with 10 components. And what we do know in advance, even though we don't know the shape of the rotors, we know their rotating speeds. And as it happens, the rotating speed is always the fundamental frequency of the harmonic series. So the first peak. And so how to obtain this spectrum? Well, we could use Fourier transform and then identify the peaks, identify the rotating speeds, and then by that identify the problematic roles. So Fourier transform has been studied for like 200 years. So that's a perfect method, right? Well, maybe not. So there are some limitations. First of all, it has a limited frequency resolution. So very similar sized roles are not separable from the spectrum. So instead of 2 peaks that are very close to each other, we only get 1 peak. And the resolution is given by frequency, the sampling frequency divided by the number of samples we have. So to achieve a good resolution, we would need to have very long measurements. And then there's the picket fence effect. So having a spectrum obtained by Fourier transform is kind of like looking the real spectrum from behind a picket fence. So we only see what's between the boards, and the highest peaks might be obstructed by the boards themselves. So maybe if we use Fourier transform, maybe we are missing some important information. And finally, Fourier transform provides no averaging. So it doesn't matter how many samples we use, how long measurement, we are not going to get rid of noise. Of course, we could use some windowing, some averaging, but if we use them, some information is always lost. So what to do? What's the solution? Hopefully the solution is subspace methods. And this is what I'm currently researching. So these methods have super resolution. In principle, they have arbitrary resolution. So they are not bound by the formula we saw on the previous slides. So that's good. Yes, separate peaks, very nice. And they are based on analyzing the autocorrelation matrix of the data. And that's something that we can quite easily calculate from the measurement data. And then we do some matrix magic in that autocorrelation matrix. We do some calculations, and by that we can split the data into signal and noise subspaces. So we can kind of pull out the noise from the signal, and we are left only with the information we need. And also, it's kind of built in the subspace methods that if we use longer samples or longer measurements, then the noise is reduced. But even these methods, unfortunately, are not perfect. So they only work with white noise. So if there's any other kind of noise in the measurements, then the whole thing is ruined. But fortunately, we can assume, or at least I assume, that in the normal operation of cardboard and steel production lines, there's only white noise. But even more, even worse thing is that the number of sinusoids has to be known a priori. So that means that we have to know the number of peaks that you can see here on the lower right before we have this picture. So that's very a kind of a problem. But fortunately, there are some methods to estimate this number. These purely mathematical methods. One of them is minimum description length. And the big question, the kind of core of this research right now is that can these methods be applied in our context? So could we determine the number of these peaks in our case and then use the super resolution methods that would solve, hopefully, this problem. And so that the common thread of this research wouldn't be forgotten, I have this punchline slide here. So what is this all about? So we have the measured thickness data, then we apply this fancy schmancy super resolution method, and we have this super accurate spectrum here, and we identify that, okay, something that's rotating 20 times per second is causing a lot of thickness variation. Then we do some calculation, and then we can, from the frequency, we can determine the diameter of the roll, which happens to be, in this case, 1033.1 millimeters. And then we look at the table that contains all the rolls that we have in our machine. And as it happens, there's a roll that's precisely of this size. So now we have identified the roll that causes the most imperfection in the end product. And then we just go to the machine and we fix that roll, or perhaps we replace it altogether. And now we have a higher quality steel or cardboard. And we didn't have to measure any rolls. We only had to measure the end product. Thanks. So are there any questions?
Samsa, where do you do the modeling? Do you do it in MATLAB or do you use something else?
Well, these examples were, or the pictures that you saw were done in MATLAB, but I'm planning to make the final method with Python. So that would be open source then, or the tools would be open source at least.
Yes. The next question, like you have shown this production line for the guardboards, and then you had these elements. So what is usually the technical shutdown time of this kind of machines? So what is the efficient use and what is the reparation time?
Well, in these machines, it depends, but usually there's, let's say, at least once a week, something needs to be repaired. So the line needs to be shut down in cardboard context. And maybe if we could identify the problematic rotors, we would only have to do it once a week. So there wouldn't be any unscheduled maintenance. So maybe we could identify this problematic rotor that's causing most of the imperfection or defect on the end product, and we could replace that before it's like too bad, like intolerable. So maybe let's say we have a scheduled maintenance on Friday, and we have identified that this one rotor is bad and it's gonna fail in Tuesday. So we can change it already on Friday, and therefore we can avoid the extra maintenance break on Tuesday.
Thank you. Is there the next question? Is there all the data available in the current measurements, or does this require more sensor installations?
Well, in steel rolling lines, they already have the required sensors, so they are constantly measuring the thickness of the end product. And that's also the case with cardboard, but usually the cardboard machines have this traversing sensor, which goes from like sideways, like left and right in the like the cardboard that's running out of the machine. So that sensor would have to be stopped so that we get like consistent measurements only from this certain spot on the paper, on the cardboard. But this has already been done with one of our partners, so that should be no problem. So it doesn't require installing new sensors, it requires a little bit of software update at most.
Thank you. We have no more questions, nor in the Q&A, nor in chat. So, Mike, back to Heidi.
Thanks. Thanks for the presentation, and thanks, Chris, for the questions.
Thank you.
To everybody else, thanks for joining us today. The presentation slides will be available early next week online. You're encouraged to contact presenters with your follow-up questions. Have a great afternoon, and we hope to see you next year at the Mechatronics Circus.